Download this code from codegive.com, link in the description below. I cannot provide you with a magic bullet solution to make your code 1000x faster with a single, universal technique. Performance optimization is highly context dependent and depends on the specific bottlenecks in your code. However, I can equip you with a toolbox of techniques, explain why they work, and provide code examples illustrating their application. We'll explore various aspects from algorithm selection to hardware considerations, and how to identify performance bottlenecks in your code. Realistically, achieving a 1000x speedup is rare and requires a combination of optimizations at different levels, often including algorithmic changes and potentially leveraging specialized hardware. Often, significant speedups are achieved by tackling the most impactful bottlenecks first. Understanding the landscape, where performance bottlenecks hide. Before diving into code, it's crucial to understand where performance problems typically arise. Consider these categories. 1. Algorithmic inefficiency, O, N, 2, O, N, etc. This is the most impactful. Choosing the wrong algorithm for the job can lead to exponential increases in execution time as the input size grows. No amount of code optimization can fix a fundamentally inefficient algorithm. 2. I/O, input/output reading from and writing to disk, network, or databases are often slow operations. Minimize I/O operations whenever possible. 3. Memory access *. Randomly accessing data scattered in memory is significantly slower than accessing data sequentially due to cache misses. 4. CPU-bound calculations * Complex mathematical calculations, string manipulations, or computationally intensive loops can strain the CPU. 5. Concurrency and parallelism * Inefficient use, or lack thereof, of multiple cores or threads can lead to underutilization of hardware resources. 6. Language-specific overhead * Interpreted languages like Python inherently have some overhead compared to compiled languages like C++ or Rust. 7. Data structure choice * Using the wrong data structure can dramatically affect performance, example using a list when a set would be more efficient for membership testing. 2. The golden rule: profile before you optimize. Never guess where your code is slow. Use profiling tools to pinpoint the actual bottlenecks. Here's how to do it in Python. Explanation **** C profile.run, main, profile_output, runs the main function under the profiler, saving the results to profile_output. **p stats.stats, profile_output, loads the profiling data. **p.sort_stats, cumulative, sorts the results by cumulative time, total time spent in the function and its calls. **p.print_stats, 20, prints the top 20 functions that took the most time. Interpreting profiler output **. The profiler will show you *calls, number of times the function was called. *time, total time spent only in the function itself, excluding time spent in functions it calls. *per call, time divided by calls, average time per call to the function itself. *cumtime, cumulative time spent in the function and all functions it calls. This is the most important metric. Per call, cum time divided by calls, average cumulative time per call. File name linino, function, the location of the function in your code. Once you've identified the bottlenecks, you can apply the following optimization techniques. 3. Optimization techniques, a deep dive. Algorithmic optimization, the foundation of speed. This is the most important optimization. If you're using a bubble sort, O, N, 2, when you could use a merge sort, O, n log n, no amount of micro-optimization will come close to the improvement you'll get from switching algorithms. Asterisk example 1, searching asterisk. Asterisk naive asterisk linear search in an unsorted list, O, n. Asterisk optimized asterisk use a sorted list or a set for O, 1, or O, log n, lookups. The set search will be drastically faster for large data sets because its lookup time is virtually constant. Asterisk example 2, sorting asterisk. Asterisk naive asterisk bubble sort, insertion sort, O, n caret 2. Asterisk optimized asterisk merge sort, quick sort, O, n log n. Python sorted, function and list dot sort, are highly optimized TIM sort, O, n log n, in most cases. Asterisk key takeaway asterisk always think about the big O notation of your algorithms. Can you use a more efficient algorithm? Consult algorithm textbooks or online resources to find better solutions. B. Data structures, choosing the right tool. The choice of data structure significantly impacts performance. Asterisk lists versus sets asterisk. Asterisk lists are good for ordered sequences and iteration. Asterisk sets are excellent for membership testing, checking if an element is in the collection, and removing duplicates. Asterisk lists versus dictionaries asterisk. Asterisk lists are good for ordered sequences accessed by index. Asterisk dictionaries, hash tables, are excellent for key value lookups. O, 1, on average for lookup. Asterisk arrays, using array module, versus lists asterisk. Asterisk array module stores elements of a specific data type, example integers, floats, leading to more compact memory usage and potentially faster access for numerical data. For numerical data, array often demonstrates faster memory access and potentially smaller memory footprint. Asterisk name tuples, from collections. Asterisk offer the benefits of tuples, immutability, lightweight, but with named fields for better readability and maintainability. Accessing fields by name is generally faster than indexing with integers. I/O optimization, reducing interaction costs. I/O operations are almost always slower than in-memory operations. Asterisk buffering asterisk read or write data in larger chunks instead of small, frequent operations. This amortizes the overhead of each I/O request. Asterisk minimize network requests asterisk combine multiple small requests into a single larger request. This is particularly important when working with APIs. Asterisk asynchronous I/O asterisk use asyncio to perform I/O operations concurrently, allowing the program to continue processing while waiting for I/O to complete. This is especially effective for network-bound applications. Asterisk caching asterisk store frequently accessed data in memory to avoid repeated I/O operations. Use libraries like functools.ru_cache for simple caching. Decode level optimization, micro-optimizations that add up. These optimizations can provide smaller but still noticeable improvements. Asterisk loop optimization asterisk. Asterisk reduce calculations inside loops asterisk move calculations that don't depend on the loop variable outside the loop. Asterisk loop unrolling asterisk manually expand the loop to reduce loop overhead, generally not needed in Python due to interpreter optimizations, but may be beneficial in other languages. Asterisk use list comprehensions and generator expressions asterisk often faster than explicit for loops for creating lists or iterating. Asterisk string concatenation asterisk. Asterisk avoid using plus equals for string concatenation in loops. It creates a new string object in each iteration, which is inefficient. Use .join, list_of_strings, instead. Asterisk function call overhead asterisk. Asterisk Python function calls have some overhead. In very tight loops where function calls are a major contributor to runtime, inlining the function code might provide a small performance boost, though this can reduce code readability. Asterisk local variables versus global variables asterisk. Asterisk accessing local variables is typically faster than accessing global variables. If you use a global variable frequently within a function, assign it to a local variable at the beginning of the function. Asterisk avoid unnecessary object creation asterisk. Asterisk creating and destroying objects has a cost. Reuse objects whenever possible. E-parallelism and concurrency, unleashing multiple cores. Asterisk multiprocessing asterisk use the multiprocessing module to run code in parallel across multiple CPU cores. This is suitable for CPU-bound tasks that are independent of each other. Be aware of the overhead of inter-process communication. Asterisk threading asterisk use the threading module for I/O bound tasks or tasks that release the global interpreter lock, GIL. Python's GIL limits true parallelism for CPU-bound tasks in a single process, but threads can still be useful for concurrency. Asterisk asynchronous programming, asyncio use asyncio for concurrent execution of I/O bound tasks. Async and await keywords allow you to write asynchronous code that doesn't block the event loop. Leveraging compiled code, escaping the interpreter. Asterisk Python asterisk write parts of your code in a C-like syntax that can be compiled into C extensions. This allows you to achieve significant speedups, especially for numerical computations and tight loops. Python can directly interact with C libraries. To compile. Asterisk number asterisk adjust in time, JIT, compiler that can automatically optimize numerical Python code using LLVM. Simply add the @JIT decorator to your functions. Number works especially well with NumPy arrays. Asterisk calling C/C++ libraries asterisk use types orgv to directly call functions from existing C or C++ libraries. This allows you to leverage highly optimized code for tasks such as linear algebra, image processing, or scientific computing. Hardware considerations. Asterisk CPU asterisk a faster CPU will obviously improve performance. Consider the number of cores and clock speed. Asterisk RAM asterisk sufficient RAM is crucial to avoid swapping to disk, which is very slow. Asterisk SSD versus HDD asterisk solid-state drives, SSDs, offer significantly faster read/write speeds compared to hard disk drives, HDDs. Asterisk GPU asterisk if your application involves graphics processing, machine learning, or other computationally intensive tasks that can be parallelized, consider using a GPU. Code style and readability, indirectly related to performance. Asterisk meaningful names asterisk use descriptive names for variables, functions, and classes. Code that is easier to understand is less likely to contain subtle performance bugs. Asterisk comments asterisk add comments to explain complex logic and the purpose of code sections. Asterisk modularization asterisk break down large functions into smaller, more manageable functions. This improves code readability and makes it easier to identify performance bottlenecks. 4. Important considerations and caveats. Asterisk premature optimization is the root of all evil asterisk don't optimize code before you've identified the bottlenecks. Focus on making the code correct and readable first. Then, profile and optimize only the parts that are actually slow. Asterisk readability versus performance asterisk there's often a trade-off between code readability and performance. Choose the right balance for your project. Document any optimizations that make the code less readable. Micro benchmarking. Be careful when micro benchmarking small snippets of code. The results might not be representative of the overall performance of your application. Use realistic workloads and data. Python version. Newer versions of Python often include performance improvements. Upgrading to the latest version can sometimes provide a free performance boost. Library implementations. Many Python libraries have optimized implementations of common algorithms and data structures. Use them whenever possible. For example, use NumPy for numerical computations, Pandas for data analysis, and SciPy for scientific computing. Testing. Always test your code after making optimizations to ensure that it still works correctly. Example, optimizing image processing. Let's illustrate these principles with a hypothetical image processing task, converting an image to grayscale. Explanation and analysis. Grayscale_Python. The most basic implementation. It iterates through each pixel, calculates the grayscale value, and sets the pixel. However, accessing pixels x, y repeatedly is extremely slow. img.load must be called, and pixel data is not directly accessible, leading to Python API overhead. Grayscale_pil. Uses pil's built-in convert function, which is highly optimized. This is usually the fastest option if you just need a standard grayscale conversion. Grayscale_numpy. Converts the image to a NumPy array, which allows for efficient vectorized operations. np. Performs the grayscale calculation for all pixels simultaneously. Data is stored in a contiguous memory block, so no time is wasted allocating. Grayscale_number. Uses number to JIT compile the loop-based grayscale conversion. Number optimizes the inner loop and can significantly improve performance, especially if you need more control over the grayscale calculation. Expected results. You'll likely see these trends. Grayscale_pil will often be the fastest, especially for simple grayscale conversions. Grayscale_numpy will be significantly faster than the naive Python implementation. Grayscale_number can be comparable to or even faster than NumPy, depending on the image size and the complexity of the grayscale calculation. Python overhead is eliminated entirely in the number case. Grayscale_Python will be the slowest. 6. Conclusion: a journey, not a destination. Achieving a 1000x speedup is an ambitious goal that typically requires a combination of algorithmic improvements, data structure optimizations, I/O reduction, code-level tuning, and potentially leveraging compiled code or specialized hardware. The key is to 1. Profile your code. Identify the actual bottlenecks. 2. Apply the right techniques. Choose optimizations that address the specific bottlenecks. 3. Measure the results. Verify that your optimizations are actually improving performance. 4. Iterate. Continue profiling and optimizing until you achieve the desired performance. Performance optimization is an ongoing process. As your code evolves and your hardware changes, you may need to revisit your optimizations.